Hello, guys. I wanted today to dive through an IGCSE Physics 2025. It's dated November 13th. So let's go through paper one quickly, check what we can do, what is given here. So at first we can check some formulas. So it's usually pretty usual. Moving on. So what do we see? Stars, yeah? The first question is about stars. So the question is about stars. The table gives information about 4 different stars. So it's presented right here. Also some colors, some masses, and evolutionary stage. Which of the stars has the lowest surface temperature? So to answer the first question, we need to know about the colors of the planets, right? So the hottest planet is the blue planet. Yeah, then there is blue-white planet, then there's the white planet, then there's the yellow, and then this is the coldest. Yeah, so this is, although we are used to think that red means hot, but in this case it's the opposite. So we choose which of the stars has the lowest surface temperature. Yeah, so which one is the coldest? So Betelgeuse is the one that meets the requirement here. Next question, which of the stars will become a supernova in the future? To answer this question, we need to take a look at this information here. So only the stars that contain more than about 8 to 10 times at least the mass of our sun can become supernova in the future. So we choose Betelgeuse for this question. It's gonna be a next supernova in the future. Next question. Sirius B and the Sun have approximately the same mass, but are different colors and in different evolutionary stages. Describe the 2 other differences between Sirius B and the Sun. So what else we can compare? The first thing that comes to my mind is that the Sun is still alive and Sirius B is dead. Is dead. It's a dead star. Um, and also to the difference. Another difference could be that it is 100 times smaller than the Sun, although the mass is similar to the Sun's mass. So I would say the size is the second difference. Yeah, Sirius B is much smaller, like 100 times smaller. We can also talk about composition here, maybe. Composition, but this is if we want to dive into some details, right? So, yeah, I think because it's burned through its fuel much faster, it's more appropriate to talk about the size here. Well, also we have question B. This is about Sirius that orbits with Sirius A as part of a binary star system. The mean orbital radius is given, the time is given. Calculate the mean orbital speed, right? So we have here you can imagine the picture. There is the orbit. There is time taken for one loop, yeah. So for one turnaround, and also we know the radius. Radius is this or this distance, yeah. So our task is to calculate the mean orbital speed. Well, at first, as usual, we go and check whether we're given the orbital speed. We are not given orbital speed. We are given, look guys, it's right here. I don't know if you can see it. It's not, it's right here, look. 2 pi times orbital radius divided by time period, right? So this one is the one. Oh, and it is a little different from the speed in mechanics, right? So we're going to take this one. And our task is to find the speed. So we just substitute all the values that we know into the formula to calculate. Nothing serious to talk about here, right? Just to calculate uh, the orbital speed, we need to multiply 2 pi by the radius and divide it by the time taken for one turnaround. So 2 pi, r is given. Make sure you are using the same units, right? Kilometers. Time is given in years, right? So we are about to convert time into seconds. So 29.7 times 10 to the power of 9. Make sure you know how to work with standard form numbers in standard form. And now coming to converting, right? So 50 years. 50 years. What do you know about 50 years? Like, we need to find how much is it in seconds. Yeah, we don't know how much, how many seconds is it. So in order to convert, think about 1 year. Yeah, 1 year consists of 365 days, right? 1 day consists of 24 hours. 1 hour consists of 60 minutes and 60 seconds, right? So this is the complete 1 year. So this thing needs to be then multiplied by 50 in order to calculate the full thing. So let me quickly calculate times 50. We got a nice result. We can also show it as a standard form number. So we can write down it like this. So I would like to use the right amount of zeros, but okay. I'm gonna write this way, times 10 to the power of 6. So this way it's easier to calculate for me, because here now, if you know the rules, we can cancel out. Yeah, 9 minus 6. So here we have like nothing. And here there are still 3 zeros left. 3 like in the power, yeah, in the exponent. So now we need to substitute the values. I'm gonna use the pi that is given in my calculator, right? It's more precise than 3.14, but it's okay if you use 3.14, you should be fine too. So I am now not even considering those tens in my calculator to check the result. So I'm going to have 0.118 times 10 to the power of 3, right? It's okay if we just convert, yeah, just multiply 1 to 3, so 3 here. It means we should move our decimal point 3 places to the right, so it's gonna be 118 kilometers per second. This way we answered the first question. I know it takes a lot of time, but we may go and check the other thing. So let's go and check what else do we have in here. Next question is about a car that travels at a constant speed. Well, let's like a couple of words about this first topic. Well, it's quite unusual that they put the astronomy question right in the beginning. So it's a nice thing for a change. So now we'll talk about a car that travels at a constant speed at 14 meters per second along the road. Calculate the distance traveled by the car. So they already gave us the formula. It's so sad, guys. We just need to substitute the average speed, make sure the units are the same, times 30 seconds. So meters per second, right? Meters, seconds. Everything is matching. So we just multiply and even we don't need to rearrange. Yeah, how sad is this? So 420. So moving on. The driver of the car sees an obstacle in the road ahead and applies the brakes. Which of these is a description of the thinking distance of the car? So you know that when we apply the brake in the moving car, the car still needs to move for a while, right? It's the first Newton's law about inertia. So, which of this is a description of the thinking distance of the car? Let's check. The distance traveled between applying the brakes and the car coming to a stop? No. Distance traveled between seeing the obstacle and applying the brakes? Yeah, looks very correct. Distance traveled between seeing obstacle and the car coming to a stop. Distance traveled between seeing the obstacle and the car coming to a stop. The car slows down. So B in here we choose. Okay, let's move on. Next question is, which of these factors would increase the braking distance of the car? Car traveling at a lower initial speed, driver being tired. Okay, one more time. Which of these factors would increase the braking distance? The braking distance is this inertia caused distance. So which of these would increase the braking distance? So the lower initial speed would decrease it. Driver being tired. Could be. Wearing tires on the car, definitely. Dry road instead of a wet road. No, dry road is a good thing. So we are considering some physical reasons, right? Worn tires on the car will definitely increase the braking distance of the car. About driver being tired, we don't know. Yeah, driver being tired is not about the braking distance, it's about the thinking distance, the question that we had before. So here we shouldn't apply B, so the answer is C. And one more question, state the only factor that affects both the thinking distance and the braking distance of the car. So what that would be, you might think as well. Well, we can say here that the only factor that affects both is the speed. So this is the primary factor that affects both thinking and braking distance of the car. Because as the speed decreases, as the speed increases, right? The distance traveled during the driver's reaction, it's the thinking distance, increases as well. And of course, the braking distance, the inertia also increases. So here we put speed. Ta-da! That's it. Let's move on quickly to question 3. I might just divide this. I don't know about it yet. So here is a simplified diagram on the electric wiring in a house. All right, a current. So you can already read, right, the schematics. So here is the source of electricity. It's AC. So active current is moving in here. So there is parameter that shows that this is an active current. There is a circuit breaker. There are lights, there are sockets, and they are in parallel, yeah, connected in parallel. So how do I understand that the thing is connected in parallel? They kind of hold each other with both hands, kind of hugging each other, yeah? Circling the both hands, both sides. So, all right, a current larger than 32 amps flows in the sockets. So larger than 32 because, okay, describe how having the circuit breaker, this little thing, in series with the socket protects the house. So here we write that circuit breaker shouldn't allow any current that is larger than 32 amps, right? Circuit breaker would break the circuit. So if I am to show you how it works, I would just copy the same, oh God, the same schematics, but I don't want to do it now. I just want to make it the shortest way possible. So just imagine that there is nothing in here, right? So there is no circuit breaker anymore because when the circuit breaker works, and it works whenever the current is more than 32, they say it is larger than 32, right? So the breaker will just break the circuit. How it works, there is probably just a fuse or whatever, so there could be different mechanism, but the thing is that the circuit is broken. Yeah, so there is no more connection between these hands. So it means the hands are not holding anymore, so not hugging anymore. And that means the sockets would be protected and there will be no current at all passing through the sockets. Yeah, so this whole thing would not be there, right? So we will break only this part of the system. So, but still the lights will be working. So this is the thing to understand here. Okay, a student suggested, question B, a student suggests that fuses could be used instead of the circuit breakers. Give two disadvantages of using fuses instead of circuit breakers. So, oh, I told you that there could be a fuse as a circuit breaker. Yeah. Well, actually, fuses are the disadvantage number one is that fuses are single use. So let's write it down here. Which color you prefer? Okay, let it be green. So fuses are single use. Here we write single use. So after every fault, they can they just die. Yeah. So they also cannot be remotely reset, but that's not the thing that we use here. And the second disadvantage I think we should talk about here is probably the thing that it works slower than the circuit breaker. So it is less sensitive to. So less sensitive in this situation, it means it is not so sensitive to higher currents. So it will work slower. Analyze, yeah, it takes more time for fuse to analyze the current. Okay. Moving on to the next question. Explain why the wiring in the house includes an earth wire. So the earth wire can protect the house from, so protection from high voltages, right? So whether we have higher voltages or some peaks in the network, in the circuit, the earth wire would save us. And also the earth wire would protect the devices we are using, and will send the short current to the ground, yeah, because it's easier way to run, not through your body, not through some harder resistance, yeah, higher resistance, but to the smaller resistance. But again, if you have questions, please let me know, okay? Next question 4. The diagram shows a force pulling a block up a ramp. Distance pulled along ramp is 3.7 meters. There is a force that acts parallel to the ramp. Yeah, you see. And also we need to understand that there is a gravity that is parallel to this height, yeah, kind of. So, okay, show that the work done by the force is about 440 joules. The formula is right here. Well, it's nice, yeah? So we just need to put the things into the formula, 120 Newton times 3.7 meters. So the units are okay, nothing should be changed here because joule equals to Newton times meters. So 120 times 3.7, we get 444. Yeah, it's about 440 joules, right? And maybe something else will be more interesting. The block gains 12 joule of energy, next question, in its gravitational store, yeah, GPE, when it is lifted. Okay, through a height. Calculate the mass of the block. For that, we need to remember that GPE is calculated as m times g times h, where m is the mass of the device, yeah? G is gravitational field strength, equal to 9.8 or to 10 on the planet Earth. So, and height is given. So our task is to calculate m, mass, right? So this is the formula we're going to use. It's not given probably because it's one of the easiest formulas. So if you're wondering, yeah, it's not given in here. So we just need to memorize it because it's quite basic. So let's rearrange quickly the formula to calculate the mass. I'm going to write here. So to find mass, GPE needs to be divided by GH. Just substitute 12 instead of GPE. Instead of G, we're going to use probably just 10, and height is 0.82. So let me, oh my God, looks a little unequal, right? So where do I put it? Just to give it some space. I like some space. Yeah, this way. So 12. Here we move the decimal place once, yeah, so to get, to get 8.2. And now we should divide 12 by 8.2. So we get 1.46. This is the mass of the block. Okay. All right, so let's move on. Yeah, one more question in this topic. A student states that most of the input energy is destroyed when the block is pulled up the ramp. Comment on the student's statement. So, yeah, to answer this question, we need to come back to the picture one more time. So a student here states that the most of the input energy is destroyed when the block is pulled up the ramp. So there is some input energy that is the energy that moves, right? So we are moving, we're driving or whatever. There is a block, right? So we're pulling. Yeah, so there is a pulling force, and the pulling force, um, pulling force dissipate, right? Actually, it is not disappearing, it is transferred into, so after the movement, the block will be up here, right? So of course, there is some energy needed to transport the block from here to here, right? And how much energy we already calculated. So there will be GPE. So the pretty big amount of energy will be transferred. So how the question is comment, yeah. So the input energy is not destroyed, right? So we can't say it is destroyed. We can say it is transferred uh, into the GPE because it's the highest point here. Yeah? So most of energy is not destroyed. It's not disappearing. It's the conservation law of energy. Yeah. So here you can write, if you write it down, so you will be so smart. Yeah. So you just need to state the law. So due to the conservation law of energy cannot be destroyed. And you should elaborate here to say that the kinetic energy of movement is transferred, yeah, into the GPE here, or the pulling energy. Yeah, maybe if it's probably it's still kinetic. There is some movement, but you can write also pulling energy. There's not much of a difference. So the main idea is to state the law here. So these were 4 questions in the IGCSE November paper. Maybe you have some questions now, let me know. It's the latest paper I could get. So please let me know if you have questions or some thoughts, share it in the comments. And here, by the way, I just saw that they gave us G actually, yeah, gravitational field strength, that it is equal to 10. So it's good that we used 10 for our calculation here. So let me know what you think about the questions. Are they okay? And also write, please, how many you could do. So we'll continue if you want this paper. If you don't want, we'll still, I think, continue solving this paper. So thank you for being here. See you. Bye-bye.